Having learned the direct method for solving simultaneous linear equations, you will notice that the order in which the equations are presented to the solution algorithm has a profound effect on the results. This ordering is what we call pivoting. Okay, so we're going to discuss pivoting. Very simple, we just simply use swap modules. So you have this function here, swap rows, swap columns, and what it does is to swap two columns. Sorry, in this case, two rows. So if you have the first and second, you want to swap, okay, you can swap it. Then swap columns, so the first and third column, so you can swap it given the index and then the matrix. Okay. And then there's another module we call this invertible. So it you just would like to check the singularity of the matrix. Okay, so this is your sheet work number 5. So what do you mean by invertible? Okay, how does it help? Okay, so basically the question is, what's the importance of invertible in pivoting, or how does it help in finding the solution of the problem? Okay, so that is your sheet work number 5. Okay, now we have here the Gauss elimination with scaled row pivoting. You will know that in this sheet work, actually, you will know that some problems or given matrix A cannot be solved using the direct method because of their order of rows and columns. Okay, so that's why we need to swap them. We need to check also what we can check using invertible. So okay, but we don't know how invertible works. Okay, so that's your sheet work. No? But we know that we need to arrange, no, we need to arrange the order of rows, okay, so that there will be, we can easily um, solve using Gauss elimination. So pivoting aims to improving diagonal dominance. Actually the answer is here. And yeah, pivoting aims to improving diagonal dominance of the coefficient matrix A. That is, making the pivot element as large as possible in comparison to other elements in the pivot row. Okay, so okay, example. So you have here. So if you notice, we have here. Uh, so the idea of pivoting is to make the diagonal dominance of coefficient matrix. So you can see here that it's not dominant, no, because you have 8 here, we have 6 here, and if you add this one, 2, 4, 8, 10, and you have 10 also in the bottom. So um, we can actually with scaled pivot, we can actually change this one, and we have here um, check in the bottom. So you see we have here -2, 8, and 6. So we have so this is the step of the um, Gauss elimination with scaled row pivoting. But let's check the output. So you have here the old A, coefficient matrix A, and then it is pivoted into this one, okay, which is diagonally dominant. So if you take the take the magnitude of 2 plus 8 plus 6, which is 14, 16, and it's greater than the summation of this one. Okay, so you can check it out. So but it's obvious if you see big numbers in the other than the diagonal, so most probably our matrix is not diagonally dominant. Okay, so we need to use this step. Okay, so then by simply using the original Gauss elimination method, we have this one. So here the Gauss pivot function is simply using um, rearranging or ordering our equations or our matrix into a diagonally dominant matrix using swap modules. Okay, so here actually we simply get the 6, 4, 8, no, and then this S comes from the equation here. Okay, so So here this value here, 648, and so actually this is the how you call this, actually let me check the um, well, there's a step actually using this one, and then and S is like a guide, a value that can help us arrange these coefficient matrix. So there's a further explanation on this in the textbook that we are referring to, so you might as well check that one. And but simply the idea here is to arrange, no? So you have to we have to arrange, no? And then these things help in arranging our equation. Okay, so then we have this one. So that's a pretty good idea. So we don't need to run through the steps here because it's quite very I mean the steps is actually simply there's a rule. Okay, so this is the rule, and then just follow some certain procedures on how to swap rows and then columns, such that this equation or these matrices A and B will not be changed, no? Okay, so given this matrix A, and then we still have the same matrix B. Okay, then and the system doesn't change that much. Okay, I mean actually they're identical. It's just we have pivoting, no? So the system still the same, identical. Okay, so these two are still identical. Okay, so we have here the Gaussian Gauss pivot function. So okay, so we have here the S. So okay, so these are the scale factors. So this will determine whether we have yeah, here the dominant diagonal dominant. Okay, so that's the scale factor. So this will help us in our things where it need to be interchanged, or the rows that need to be interchanged. So you will see here, so we have S, and then actually we can check whether the matrix is singular or not, okay, by getting this one. So the absolute of D1 should be greater than the tolerance, but I suppose you don't need to know this for now. And if you would like to go deeper, so you can actually, if you want to apply this method to your software or program, so you can probably you might need to include this, because otherwise your Gaussian may not there might be some problem, no, along the way if you don't so some technical issue. Okay, so then we have here swap rows. Okay, so if you notice the swapping module, so this is a function we defined earlier. Okay, swapping. Okay, and then we have the elimination, which is quite familiar to us. Okay, and then this is also a way of checking whether the matrix is singular, another similar in this case. Okay, and then having known this one, so if you notice we have the P, and if P is not equal to K, okay, P here, okay, if it's arg maximum, so so these are some of the function we use to get this one. If you notice, this is actually here the one in the to determine whether it is diagonally dominant. Okay, then if this is with a value, any value, either positive 1 or negative 1, it should be 0. And if there's a change here, then plus K, so therefore making it not equal to K. So if there's a value here, and then therefore this will not do, then there's a swapping. Okay, so the scale factor, and yeah, so there's a swap. Okay, so that's a case until such time we get the scaled uh, Gaussian method. Okay, so this one is quite familiar to us. Okay, the back substitution method, and we can try the example. So we have here A, I forgot to show to you the A. So you have 2, negative 2, 6. So this is the same as the manual steps, okay, here. And then you run the method. I hope we haven't run this one, okay. And then okay, so there's a tolerance here, but you can later you can ignore that one. Okay, sorry, there's a swap rows. Oh, we haven't run the swap rows module, sorry. Okay, so you just go back and just run this. Also, you may want to run this one. Okay, and here we have uh, mm, okay, 1, negative 1, and 2. Actually, it directly solved the value of your x, 1, negative 1, and 2. So, so which is this one? Okay, so if you manually solve this one, the result is 1, negative 1, and 2. So, but it doesn't show us the result of the swapping, but it's okay. So as long as here we apply the swapping inside, so it might take a while before we can show the we can show the swapping. Actually, yeah, swapping. Okay, so that's it, no? So that's for the pivoting, and this is the same as the. Actually, here it will show us I made some short debugging here, so you might ignore this one. So you see here the steps of the pivoting. So how it derived to 1, negative 1, and 2. So this is the same code as the above. So you notice from here A, this is our coefficient matrix A, and if you see there's a 648. So this is the scale factor, and then in the next iteration P1 P and K are equal, so then you see here there's a swapping happen. Okay, so the 4 is now becomes okay, this the second becomes the first row. Okay, so they swap, no? And then the result B, so also B swaps, no, respectively, because 16, so it also changed to the second. And then the scale factor is 4, 6, 8. Okay, and then you have the elimination. Okay, elimination. So then we have the new A. Then and then okay, so you have B. Then they're the same, and then there's still swapping happen. Okay, and then until such time you get another elimination. Then until such time you get uh, when P and K are not equal anymore, okay, then you will proceed to the next step. Okay, so which is the backward method, or the backward substitution, and then you will get the result here. Okay, so this is basically the same as the above, okay, here, and yeah. Okay, so that's for the Gauss pivot, or the pivoting step. And our next topic, it will be LU pivot.